Today I am going to deal with chemical reaction equilibrium. This is one of the most important chapters for chemical engineers because we are going to see how to design chemical reactors. Now, suppose you want to design want to design a reactor. For example, you got a reaction A plus BB giving CC plus DD. Okay, we are going to start designing a reactor. There are three questions which are to be answered before you start designing a reactor. First, is it feasible? Is this reaction possible? Will A plus A and B give C plus D or not? If it's going to give, what is the optimum temperature? What is the optimum reactant ratio? Okay, and other parameters. So this is the area of thermodynamics. So you make a thermodynamic analysis and say that A plus B will give C plus D. It's possible. What is the optimum pressure? What is the optimum temperature? Reactants ratio. They all can be designed from thermodynamics. So for thermodynamics, first says this is possible and under what conditions of this pressure, this temperature, this reaction ratio. Second question, how fast it is going to take? Will one take 1 day, 10 days or 1 hour? Speed of reaction. Speed of reaction. How long should I wait? This is the branch of chemical reaction engineering. Reaction engineering. So you make this analysis, first thermodynamics, then the reaction engineering says how fast is react possible. Okay. Then it is possible, it is also fast enough. Third question is economics. You go and tell industry, I got a reactor, I got a chemical reaction, I can design a reactor for you. First thing is what is the cost? Money involved. So am I going to use a gold catalyst or a platinum catalyst? Going to be very costly. So economy is possible important. So the first two things are engineering, third is economics. If all these three factors are satisfied, then you can go ahead with the reactor design. Now, the number of derivations and all, which I am not going to deal with. Derivations all you can do, but I'll broadly tell you how to go about designing a reactor. Earlier, if you remember, I have told you about how to design a reactor. Steady state design and unsteady state design. Steady state design, then unsteady state design. And you have seen that if you find out the payback period, sometimes unsteady state design is better than the steady state design. That's I will give you a particular topic. Now, we can broadly define classify reactions as one, gas phase reactions. Gas phase reactions. For example, methane plus oxygen giving carbon dioxide plus water. I am not balancing the equation. Then sulfur dioxide plus oxygen giving sulfur dioxide. Manufactured sulfuric acid. So a number of gas phase reactions are there. This is the first gas phase. Second, you have got heterogeneous reaction or gas heterogeneous reactions. This is homogeneous reaction because everything is in the same phase. Heterogeneous reactions, for example, carbon plus oxygen giving you carbon dioxide. This is solid gas, so it is a heterogeneous reaction. Third, we have got liquid phase reactions. Liquid phase reactions. For example, benzene plus nitric acid, benzene plus nitric acid giving you nitrobenzene and water. So this is a liquid phase reaction. So we can broadly classify reactions as gas phase reaction, heterogeneous reaction and liquid phase reactions. Now for all these things, we start with calculation of standard free energy change. Delta F naught T. That is equal to minus RT ln Ka. This is the most important equation. Delta F naught is the standard free energy change at temperature T. What is standard? What does it mean? Standard means gases at atmospheric pressure is supposed to be in the standard state. Like that, for liquids at the web pressure at the temperature is supposed to be the standard states. So that you can go through. This delta F naught T can be easily calculated from standard calculations. If you look into a book called Thermodynamics, we will see how to calculate delta F naught T. Delta F naught T is minus RT ln K. R is a gas constant. It is 8.314 kilojoules per kilogram mole degree Kelvin. Temperature is in degree Kelvin. Okay. So this will be in kilogram moles, kilojoules per kilogram mole. Delta F naught T at the temperature. Suppose the reaction is taking place at 100 degrees. What is the change in standard fuel change at 100 degrees? You have to calculate. This calculation part of it, you can refer to my book and you can see very easy. I will not waste my time on that. So it minus RT and K. Therefore, if you know the standard fuel change, R you know, time know, you can calculate K. This is the reaction velocity. It's an equilibrium constant, okay, based on activity. This is your, once you know K, now for our reaction AA plus BB giving CC plus DD. AA, K is given as AD power D, AC power C, A power A, AB power B. Well, what is this activity? Activity is nothing but fugacity divided by the standard fugacity. Now, let me not go too much into this. Okay, activities, fugacity, partial fugacity, fugacity at steady state. Now, for gas phase reactions, as I told you, sulfur dioxide plus oxygen gives sulfur dioxide. Okay, methane plus oxygen. So, for gas phase reactions, activity is normally equal to the partial pressure. Activity equal to partial pressure. Okay, then that means this Ka nothing is equal to Kp. That is equal to P power Pd power D, Pc power C, Pa power A, Pb power B. P is the partial pressure of D in the gas equilibrium mixture. Pc is the partial pressure of C in the equilibrium mixture. Pa and Pb. The A, B, C, D are these constants. Now partial pressure can be written from, except for high pressure reactions, you can use your Dalton's law and write as Ka equal to Kp equal to Yd power D, Yc power C, Ya power A, Yb power B into P power C plus D minus A plus B. How do I get this? Partial pressure is nothing but your mole fraction times total pressure. So I have written for each component Pd equal to Yd into P. Okay, and Pa equal to Ya into P. So we get this C plus D minus A plus P. Now, look, if you look at this, if C plus D equal to A plus B, what happens? You get P power 0, that is 1. Therefore, for reactions where the number of moles in the left hand side and right hand side, reactants and the products are same, pressure will not have any effect. However, if A plus B is greater than C plus D, for example, N2 plus 3H2 giving you 2NH3. 3 plus 1, 4. 4 is greater than 2. 4 is greater than 2. That for such reactions, higher the pressure, for such reactions, okay, C plus D, higher the pressure, greater the conversion. So, for the decrease in number of moles is based on Le-Chatelier's principle. A plus B gives is this as a difference. As the decrease in number of moles, then higher the pressure. That's why you get ammonia. This is at high pressure reaction. Okay, and if otherwise A plus B is less than C plus D, then lower the pressure by higher the conversion. Normally, when you say conversion, we have to specify. Suppose that on two reactants, how do you specify which conversion with respect to A or B? We take the limiting reactant. What is the limiting reactant? Suppose this is A and B. Suppose I send A in corresponding one A mole, B is excess reactant. So A, without sending the stoichiometric ratio is called a limiting reactant. Suppose this is A equal to A, B is suppose more than B, suppose then more, then A becomes a limiting reactant. Conversion is always with respect to the limiting reactant. Say 20% conversion means with respect to A because it is a limiting reaction. There is another thing of yield. Yield is with respect to products. Conversion is with respect to reactants, that to a limiting reactant, and yield is with respect to the product. Here again, two products are there. Which product? See, I may be interested in C, I may be interested in D. Suppose C is my product of interest, then my yield is always with respect to C. So yield is always with respect to the product, conversion with respect to the reactant. This should be very, very clear. Conversion and yield. Conversion with respect to limiting reactant and yield is with respect to the product of interest to you. Okay? Now, this is for your this reaction. What is this? Gas phase reactions. Then if we take gas solid reactions, as I told you, carbon plus oxygen giving you carbon dioxide. This is solid, gas. For solids, activity is 1. Activity is for 1. Therefore, you will get here for this reaction Kp equal to P power CO2 for this reaction by P power O2. Okay, for this reaction, C plus O2, please C plus oxygen give you CO2, P this is 1 mole, this is 1 mole, so P power 1 people. Okay, or this is Y CO2 by Y O2 and P power what? Pressure power 1 minus 1. Okay, now this is for the gas solid reaction. For example, you take SO2 plus half O2. That comes down, okay? Now, third is liquid phase reaction. Liquid phase reactions. Phase reactions. We can show that for liquid phase reactions, A is approximately equal to X, the mole fraction in the liquid phase. Therefore, Ka will be equal to Kx. For the same reaction, A plus Bb giving Cc plus Dd. Okay, so it will be A d power A d is xg power d, xc power c, xa power a, and xb power b. So here for liquid reactions, pressure does not have any much effect. Therefore, this is your reaction velocity constant. So you can always calculate Ka, Kb, and Kc. Now, before going any further, now we can calculate the equilibrium constant. Now, two types of reaction, exothermic reaction and endothermic reaction. In the industrially, about 80% or more are exothermic reactions. Okay, for exothermic reactions, you plot the equilibrium conversion. What is equilibrium conversion? The maximum conversion possible at that pressure, that condition. What is the temperature? Okay, equilibrium conversion temperature. For exothermic reaction, it will be like this. The curve will be like this. That means as temperature increases, conversion will decrease. Therefore, for exothermic reactions, as higher the temperature, lower the conversion. Okay, and I told you most of the reactions are only exothermic nature. For endothermic reaction, we take equilibrium conversion versus temperature. It will be like this. Curve will be like this. That means higher the temperature, higher the conversion. See, higher the temperature, higher the conversion. Here, higher the temperature, lower the conversion. Therefore, for exothermic reactions, higher the temperature, lower the conversion. For endothermic reaction, higher the temperature, better the conversion. Now, according to kinetics, speed of reaction depends on temperature. K equal K naught E power minus E by R, A by RT. So, according to kinetics, higher the temperature, faster the conversion. But here in exothermic reaction, what happens? Higher the temperature, lower the conversion. What are you going to do? It's a compromise. Kinetics says higher the temperature, faster. Thermodynamics says higher the temperature, lower the conversion. What are you going to do? You have to make a balance between the thermodynamics and thermodynamics and reaction engineering. That is solved by people. Sit down in the design room and find out what is the best temperature possible. Make compromise between kinetics and thermodynamics. Now here again, normally we've got two types of reactors. That is, one is called isothermal reactor and adiabatic reactors. Adiabatic reactor. Isothermal reactor means what? Reactor temperature has to be kept fixed. You have to keep the temperature constant. For example, you've got the equilibrium conversion versus temperature. I can operate at this temperature. That means this will be the conversion. This temperature, this will be the conversion. This temperature, this will be the conversion. So I can maintain this temperature in the reactor. That means what? I should have some controllers, temperature sensor, then transducer to convert that temperature into electrical signal, I get controller, the final control limit, all these things. Normally, in industry, the cost of control systems and instrumentation is about 20% of the capital cost of the equipment. Suppose the equipment costs 100 rupees, I would spend only 20 to 30 rupees on the instrumentation part of it. So, you have to spend some money for instrumentation. Now, on the other hand, adiabatic reactor means what? It be going, it has no temperature converter at all. For example, I will tell you how it looks like. Adiabatic reactor, equilibrium conversion and temperature, just like this. What they do in adiabatic reactors, first reactor, they will convert like this. Cool it to a little temperature, then take it here. So you conduct the temperature at this first reactor like this, first reactor. Then you cool it and go to the second reactor. Then you cool it and come back to third reactor and forth. So you can reach this conversion in number of stages. Here adiabatic reactor, first stage, second stage, third stage. So you can have 3 reactors in series adiabatic reactor, no control system at all. Just allow it to go control the adiabatic temperature, reach adiabatic reaction temperature. So you can do in 3 stages. Whether it is adiabatic reactor or isothermal reactor, it has to be designed by economics. So I will stop with this and we'll continue to my next class further better. Okay. You please have any doubts, as I told you earlier, you can always contact me and find out. Okay, and you are interested in any particular specific reactions and all, you can study. What I am going to take in next 2 classes is conversion of sulfur dioxide to sulfur trioxide. I am going to study the reaction completely. What happens to reaction ratio, what happens to the temperature, how does the pressure affect. All these parameters will be taken into consideration in studying the analysis of sulfur dioxide plus oxygen giving you sulfur dioxide. It's using a vanadium pentoxide catalyst, V2O5. Okay, we'll stop with this for today. Okay, we'll see you later.